I'm Alex Thomas. I'm one of the lecturers in geosciences, and I'm going to be kind of broadly taking you for this um, uh, uh, session, as it were, online for how the ocean is changing in this kind of corals in a changing ocean um, course. Um, So before we describe how it's changing, we're going to need to learn also how the ocean broadly works from a kind of a physical perspective and also some ocean chemistry, because things like the ocean temperature and the ocean chemistry, particularly with its acidity, are really important for the impacts on coral reefs. So there's going to be a few kind of short, hopefully, videos which I want you guys to watch. So please watch those. And then we'll have a tutorial exercise at the end, which will either be online or in person, looking at how we might kind of mitigate some of the effects of the changing ocean on coral reefs. But before we get into kind of the meat of kind of like how the ocean works, I guess all of you on the course think that the ocean is important because that's where kind of corals live. So it's important. The ocean is obviously important for the things that live in it. But actually, the ocean is really important for the climate system uh, um, itself. So I think I'll just give you a brief overview of some of the reasons why kind of the ocean on its own is important, irrespective of the things that live in it. So first of all, the ocean is really big. So it's most of the Earth's surface is ocean. I guess this kind of satellite composite actually quite unusual to see kind of like satellite composites of the Earth actually with the clouds in them in this way. So actually quite a lot of what kind of space sees are clouds, but actually also when it's not cloudy, the vast majority of kind of incoming solar radiation hits the ocean. Okay? And the ocean is really good at soaking up that heat energy because it's really big, so it's got a large surface area, but it's also fluid, so that heat can mix down into the depths of the ocean, and the ocean is quite deep, almost 4 kilometers deep on average. There are parts which are over 10 kilometers deep. So heat can be a large amount of heat can be stored in the ocean. And just to kind of like compare, kind of like I guess the thermal masses of the two, the mass of the ocean is over 300 times the mass of the atmosphere. So it is a really substantial thing that can store a lot of heat energy, and that's going to become later on. But also, the ocean can store a lot of other stuff, and of particular kind of relevance to climate change is carbon. So looking at the carbon cycle now, because the ocean is really big, but also, and as we'll see in a future video, that the ocean can actually take in a lot of carbon dioxide. So carbon dioxide is quite soluble in water. And that has a whole variety of impacts on its chemistry. But from a I guess a global warming perspective, the ocean is really important because any CO2 that makes it into the atmosphere will exchange with the ocean. And because the CO2 is so soluble in the ocean, we can store, the Earth system can store a huge amount of carbon dioxide in the ocean. So it's one way of thinking about kind of the carbon cycle is not that we're putting lots of carbon dioxide into the atmosphere and that's determining how much global warming we're getting. It's really we're putting carbon dioxide into the atmosphere ocean system because the fluxes between the two are quite high because there's quite a large surface area of the atmosphere and ocean exposed, so it's very easy for gases to exchange across that. And kind of quite fortunately, there's a huge like capacity in the ocean to soak up carbon dioxide. So I guess this is I guess an old image now you might be familiar with from the IPCC climate report. But one thing that I guess I would point out, I guess just to go through the flow of kind of what we've done here. So we have, if I just kind of burned fossil fuels down here. So we've burned a huge amount, almost, I guess, almost 400 gigatons of carbon. I guess probably by now it's probably got over that 400 gigatons of carbon. Now that has gone burnt into the atmosphere via, I guess, this arrow here. But actually, if you look at where that's gone, okay, you can kind of try and kind of account for that kind of amount of carbon being released. It's not the same as the amount that's in the atmosphere. Okay? Some of that, large proportion of that, has actually gone into the ocean. So there's a constant exchange. So carbon dioxide is constantly dissolving in and exsolving out of the ocean, but there's been a net flux of carbon into the ocean. So we've got this extra carbon dioxide. In that case, it's actually not being held in carbon dioxide form, it's in a different chemical form, mostly in the bicarbonate ion, but that carbon has ended up in the ocean. So the capacity of the ocean to store carbon is really important. If you just look at the relative kind of stocks of carbon in all the different reservoirs we have, you can see that this little summary table I've got over here on the right, that the ocean is vast in terms of its capacity to store carbon compared to the other reservoirs. So in terms of the atmospheric carbon dioxide concentration, certainly on maybe much longer timescales than we're experiencing in our current global warming, kind of human kind of driven climate change. It's actually the ocean that determines the atmospheric concentration of carbon dioxide, not the other way around. So just mentioning a bit about kind of global warming and this kind of carbon dioxide, I thought I'd just quickly introduce really simple model that can be used to explain kind of what are the actual drivers behind current climate change. So here is a simple model of the Earth's kind of climate system. We have the sun over here, which is very hot. So this is I'll try it over here, hot. Okay, and because the sun is an object that is hot, it's got a very high temperature, it will emit electromagnetic radiation proportional to its temperature. So the hotter it is, the more radiation it gives out. And also, the hotter something is, the shorter wavelength the mean energy that's given out is. So we've got short wave radiation coming from the sun. So this is short wave radiation coming from the sun. So it's got I guess, a peak intensity around visible light. And that's coming and that's hitting the Earth. Now, some of that energy gets reflected straight back out into space because some parts of the Earth, like these clouds here and this big ice sheet down at the bottom, these are quite reflective. If you've ever been out for a walk in the snow, you can get kind of sunburnt on the bottom of your chin if you don't have a nice beard like this. So some surfaces are quite reflective. The ocean, as it turns out, is quite dark, so it's not reflective. So some of that energy gets absorbed by the Earth's surface. That causes the Earth to kind of like heat up, and that allows the Earth to have a temperature because it's getting this energy from the sun. There are other energy sources within the Earth, so there's some radioactive decay kind of within the Earth's crust and deep in the mantle, and some gravitational potential energy kind of from I guess actually no, there's not gravitational potential energy. There's kind of tidally dissipated energy from the kind of the solar system, that kind of stuff. But anyway, these are really small compared to the amount of energy coming in from the sun. So we can kind of ignore them because they're not relevant on a global scale. So the Earth heats up, allows it to have a temperature, and any object that's got a temperature above absolute zero, that will emit radiation. So that the Earth heats up, it becomes warm. Fortunately, not as hot as the sun, and because it's not as hot as the sun, it gives out less radiation from its surface. These arrows here, and because it's at a lower temperature, the wavelength that energy gives out is at a lower or longer wavelength. So it's around kind of infrared rather than visible light. And that's important because the atmosphere of the Earth is transparent, or mostly transparent, to shortwave radiation. That's why we can see the sun, because we can see the visible light shining through the atmosphere. But it's actually mostly opaque to long-wave radiation. It's not completely opaque, so some energy does escape into space, but it's a little bit opaque to this longer wavelength radiation, and that leads to the kind of greenhouse effect. Now, this is kind of, I guess, more mathematical representation of that simple model. So if we just kind of go over the key features of this, so we've got this incoming energy from the sun, this solar flux, this F0 here, and that's actually divided by 4 because the energy that gets kind of intercepted by the Earth coming from the sun, that's effectively the area of the Earth's shadow, and that's spread out over the surface area of the Earth's, which is a sphere. The ratio between a circle and a sphere is 4 in terms of the surface areas. So that's the energy coming in. Now, some proportion of that will be reflected from the surface or from clouds. So the proportion reflective is this alpha term here. So the albedo. The albedo. So that's the reflectivity of basically the planet, planetary average. So if the planet was a complete kind of perfect reflector, alpha would be 1. The amount of energy coming in would be completely reflected, and no energy would be absorbed by the Earth's surface. Now, the Earth isn't a perfect reflector, so because alpha is less than 1, the surface can receive some energy. That causes the surface to have this temperature. So this is this Ts. Now, because the Earth is an object, it will radiate energy away proportional to actually the temperature to the power of 4 times this constant. So this is the Stefan Boltzmann constant. So that's just a physical constant that describes how much energy an object will radiate away due to it having a temperature. So the hotter an object is, the more it will radiate away. So that gets kind of sent off out towards space, but it is intercepted by the atmosphere here. So there's interception in the atmosphere, and that's because the atmosphere is mostly opaque to long-wave radiation. And that opaqueness is this epsilon term here. So the amount that escapes up into the atmosphere is basically the amount that is emitted from the surface minus the amount that the proportion of absorbed of the atmosphere. So this epsilon is basically the opaqueness of the atmosphere, how much it doesn't let light through effectively. So that means that that energy that's not let through, that has to be absorbed by the atmosphere. The atmosphere then heats up, okay, and it actually doesn't emit energy perfectly in the same way that the Earth's surface does. So it has this term epsilon in term, which actually is related to the amount that it kind of absorbs compared to like a perfect object, is the same for absorption and emission. So we then have energy because the atmosphere is now warm. It's warm because it's absorbed energy coming out from the Earth's surface here. That gives it a temperature, and then the atmosphere then radiates energy up and down towards space and back towards the Earth's surface, where the Earth's surface can absorb it. So what we can do is we can start to kind of at the top of the atmosphere, we can start to balance all of these terms. So we can say, add up all of the downwards going fluxes. So it would be S divided by 4, and then this would be minus alpha divided by 4 minus this term here, minus this term here. And then we can also add up the downward fluxes at the bottom of the atmosphere and do the same thing. So it would be, we get a slightly different kind of equation. And then we can say that if the system is in balance, if nothing is changing, if the temperatures are gradually increasing or falling, if the system is in steady state, the fluxes in and out, so if we add up all the fluxes down, they should all equal 0, because the fluxes into, fluxes in, and the fluxes out should all equal 0. And that will effectively give us 2 equations, which we can rearrange into this kind of equation here. And the neat thing about this equation is it allows us to kind of predict the surface temperature of any planet and what we can see that it's dependent on the flux of energy from the sun, which is determined by the power of the sun and our distance from it, the reflectivity of the planet, and the emissivity of the atmosphere. Everything else, 2, 2, 1, a quarter, Stefan Boltzmann constant is a constant. So what this allows us to show now is that the Earth's climate, if we change any one of these parameters, so if we increase the power of the sun, see that's on top of this equation, so the temperature should go up. If we make the planet more reflective, if this alpha goes down, then this term will get, sorry, if the planet becomes more reflective, alpha will go up. Alpha goes up, more reflective planet, more energy gets sent out to space, the planet will cool down. And likewise, if we make the emissivity of the atmosphere greater, or the opaqueness of the atmosphere, if that goes up, okay, then this term at the bottom will get smaller, this term here will get smaller, which means that the surface temperature will go up. And we can kind of see that in our records of past climate change. Anytime when we've had large ice sheets, the albedo has been high, the planetary temperature has been low. The power of the sun does affect climate, but actually the amount that's been changing over the last kind of 100 years or so is not really sufficient to explain the temperature changes. Also, that the power of the sun changes on an 11-year cycle, and we just haven't seen that in the temperature record. So let's have a quick look at these temperature records now. So we've got atmospheric CO2 rising nice and smoothly, some annual variability, and we can see that the temperature record, so this is the surface temperature of the Earth, that's also kind of followed a similar pattern. Now there's some detail here that's not reflected. So one of the criticisms made by climate skeptics is that some of this variability between years, that's clearly not driven by carbon dioxide. So people see things like maybe this changes in the rate of temperature change, and they say, oh well, it can't be CO2 that's causing this temperature rise. And actually, I mean, that's a kind of a reasonable statement to make if you kind of look at the data. But actually, although all of these different research groups in the UK and the US, actually, they all agree very well. See all of the curves for temperature, they all agree very well. So it looks like we can measure the surface temperature of the Earth really well. And we can, but the surface temperature of the Earth isn't a really good indicator of the heat content of the planet. And that's because the ocean is so big, it stores so much of the heat energy. And if we actually have a closer look at some of the other parameters that have been changing in the Earth system. So again, we've got the CO2 rise here, nice and smooth. You can kind of see a little bit more clearly now the annual cycles due to photosynthesis and respiration. And I guess the Earth's surface temperature, again, that's rising up here. And you can see even more research groups here really measuring the Earth's surface temperature very precisely. But if we look at the ocean, I just want to look at sea level. So sea level appears to be rising much more smoothly. It kind of agrees much more well with the carbon dioxide record. And the sea level has been rising for a number of reasons. One of them is that ice has been melting on land because it's getting warmer, and that's been going to the ocean. But actually, the main reason for this sea level rise is actually that the oceans are warming up and they're just expanding because of thermal expansion. The amount of actual meltwater going to the oceans is, not insignificant, but the main reason for this rise is the thermal expansion. And we can see that at the top right up here. So these are estimates of the ocean heat content. And that these are actually measurements which are much harder to make. It's very difficult to measure the ocean because it's a three-dimensional kind of thing. We can't see through it. So if heat is being kind of mixed down to depth, that's quite hard for us to measure. But we can see that there is this gradual increase in thermal content of the ocean, and that is kind of where we think some of these kind of ups and downs in the interannual variability of global surface temperatures is because the heat that's kind of accumulating on the planet is actually being moved between different reservoirs. It's not kind of the total heat of the Earth going up and down. So this is important for this course because these extremes in heat fluxes between the atmosphere and the ocean are really important for the corals that are living in the ocean. And we'll come on to that kind of later on to the course. And just to kind of to give a bit more indication of kind of the relative importance, there have been some estimates apportioning this heat content of the planet between the atmosphere and the ocean. And actually, you can see here that most of the heat that's gone into the Earth over the last kind of 50 years or so has actually been accumulating in the ocean rather than the land, because the ocean is so much bigger than the land, both in its area but also in its ability to move heat into the deep parts of the ocean. So just to summarize, the planet's been getting warmer. This is mostly due to atmospheric CO2. Most of that is in the ocean, and that ocean warming is going to have impacts for the corals that are living in the ocean. We'll come on to that in later parts of the course. And yeah, just to summarize the main point, that the ocean is really big, so it's also important for the climate system by itself, irrespective of the things that are living in it. Okay, so the next video will be looking at the mechanisms or the physical structure of the water column and some of the chemistry that's going on in the ocean, particularly with regards to CO2. So look out for that video, which will be posted somewhere near this one. I'll stop there. Bye-bye. Take some notes.